What is an engineered living material? What's an engineered biological entity? They've made a ton of biological synthetic creatures, and most people call them aliens from all these other planets. Most of you out there didn't call it synthetic biology. You called him Rob, the EBE.
Let's Google engineered biological entity. And we're going to click on the images. Rob the EBE is an engineered biological entity with synthetic biology and something called tissue engineering, where they can 3D grow in vivo inside of you a new organ if they needed to. Microchips are no longer necessary for the synthetic biology at a nanoscale with biometric systems. Now let's Google DARPA biohybrid. We have with DARPA engineered living materials. For example, this cyborg cockroach. Let's click on the link. This cyborg cockroach could be the future of earthquake search and rescue. From drivable bionic animals to machines made from muscle, biohybrid robots are on their way to a variety of uses. So how do they do this? He did this by attaching electrodes to parts of the insect's body, which can be controlled by either a remote human operator or the onboard computer. Electrically stimulating touch receptors or muscles on a cockroach's left side makes the insect move right, and vice versa. We use the insect's natural behavior to induce a turn, says Sato. Stimulating left and right movements simultaneously propels the cockroach forward. The group's latest prototypes use navigation algorithms run by an onboard computer to control the insect's direction according to what the infrared camera detects. Obstacle avoidance is achieved by monitoring the cockroach's motion. If it is brought to a stop by an obstacle, the navigation algorithm will direct the insect to move away from the blockage and find a way around it. I will leave the link in the description for those who want to read this entire article. But for now, let's go to DARPA's official website. Engineered living materials. The Engineered Living Materials (ELM) program seeks to revolutionize military logistics and construction in remote, austere, high-risk, and/or post-disaster environments by developing living biomaterials that combine the structural properties of traditional building materials with attributes of living systems, including the ability to rapidly grow in situ, self-repair, and adapt to the environment. Living materials could solve existing challenges associated with the construction and maintenance of built environments, and introduce new capabilities to craft smart infrastructure that dynamically responds to its surroundings. Advances under the ELM program could also improve methods for manufacture and maintenance of military systems such as tanks, planes, and ships. ELM specifically aims to develop design tools and methods that enable the engineering of structural features into cellular systems that function as living materials, thereby opening up a new design space for building technology. The program aims to validate these new methods through the production of living materials that can produce, self-organize, and self-heal. Such engineered living materials would also have the ability to respond to their environment in designed ways, self-repairing in response to physical or other stresses, or detecting the presence of specific stimuli, such as hazardous compounds. The program has two technical tracks that balance near-term opportunities with long-term capabilities. The first track seeks to deliver hybrid materials composed of inert structural scaffolds that support the growth of living cells. These platform technologies are intended to be scalable and generalizable to support near-term transition out of the laboratory. The second track aims to discover fundamental engineering principles that enable the genetic programming of structural features into biological systems. Performer teams seek to invent methods to program the development of multicellular systems with specified and tunable patterns and shapes.